Example 3, analyze the graph of the rational function r of x is a quadratic divided by a monomial. To begin, note the leading coefficients are positive ones, and the degrees of the numerator and denominator are 2 for the numerator, and for the denominator 1. So m is 1. Now, in this case where n is 1 more than m, that's case 3. And in case 3, which again is degree of the numerator is 1 more than degree of the denominator, as x gets very large, x goes to negative or positive infinity, the n behavior will resemble the power function 1x to the first. We'll go over that in more depth a bit later. In other words, there will be an asymptote whose equation will be a linear expression and a linear equation for that boundary line or asymptote. All right, step 1 is to factor the denominator and numerator if possible. So the numerator looks factorable as a product of two binomials. 2 times 1, everything's addition. And the exponents or multiplicities on the numerator factors are ones, odd, and so the graph will intersect at the numerator zeros of -2 and -1. The denominator is just x to the first. And when the denominator is 0, which is the number 0, has an odd exponent, odd multiplicity, then the graph's going to have opposite infinities as x approaches 0, which is the denominator 0. So we're going to have opposite infinities as x approaches 0 from the left, from the right. Okay, state the domain, which is x can be any real number except for the denominator 0, which is 0. So the restriction is 0. Second step, if possible, simplify by dividing and canceling, which is not possible here. So we already have simplest form and factored form. So no simplifying possible. Next, intercepts. For x-intercepts, where the graph would cross the x-axis, then y would equal 0, or since y is r of x would equal 0. And function values or r of x values are 0 if the numerator of the fraction is 0. So that would mean that the numerator x plus 2 times x plus 1 would equal 0 for x-intercepts. And solving that, we get x equals -2 or x equals -1. So we can start graphing those 2 points at -2 and -1 close together. For the y-intercept, every point in the y-axis has x equal to 0. So if x equals 0 and we evaluate the function for x equals 0, the numerator becomes 2, since all variable terms become zeros. But then we have division by 0, which is undefined. So there's an input of 0, but no output. So there's no point on the y-axis, no y-intercept. Step 4. Are there any vertical asymptotes? VA. Vertical asymptotes come from the denominator 0 or zeros. Here we have the denominator 0 is the number 0, so x equals 0 is the equation of the vertical asymptote, and this is the equation of the y-axis. So we have a boundary line that is vertical, and a graph of a rational function will never intersect, never cross a vertical asymptote. Step 5 is to determine if there's any horizontal or oblique asymptotes. Now, we have case 3, so there's no horizontal asymptote, but there is an oblique asymptote because of this being case 3 where n is 1 more than m. And to find the equation of the oblique asymptote, we have to do division. Now, there's no space here, so we're going to copy this to another area to do the division. All right, so let's go to a new paper here. And divide x, whose constant is understood to be 0, so let's put a plus 0, 0 placeholder there, and divide into the quadratic. So this is long division, and we divide the leading terms, x squared divided by x, which you can do mentally. That's equal to x to the first. So x times x and x times 0 gives x squared plus 0x. Insert parentheses and subtract. So that's 3x. Now the divisor has 2 terms, so we want the new dividend to have 2 terms, so bring down the 2 and then divide 3x by x. That is equal to positive 3, so plus 3 in the quotient, 3 times x and 3 times 0. Insert parentheses and subtract. So we get a remainder of 2. Remainder r is 2. So remember that the original dividend, x squared plus 3x plus 2, divisor of x, is equal to the quotient polynomial, which is the x plus 3 plus the remainder over the divisor, which is x. So this equals 1x plus 3 plus remainder of 2 divided by x. Now let's look at what happens as x gets very large. And by large, we mean x goes to negative infinity or x goes to positive infinity. In other words, when x is large, the absolute value of x goes to infinity. And there's 2 cases where x is large, negative, x goes to negative infinity. The fraction is positive 2 divided by a large negative number, which is a very small negative value close to 0. So the rational function, or the y value, is going to be approximately x plus 3, because you're adding 2 divided by a large negative number is close to 0 and negative, so we'll say 0, negative, which means small and negative. In other words, you're subtracting from x plus 3 a small amount. So the y value or function value will be close to the approximate value x plus 3. On the other hand, if x goes in the opposite direction, x is very large, positive, x goes to positive infinity, then the denominator will be positive 2 divided by a large positive number is very small and close to 0 and positive. So r of x, the function values or y values, will be approximately x plus 3 plus close to 0 and a small positive amount, which we can ignore if we're approximating. Also, let's look at this. The original dividend x squared plus 3x plus 2 divided by x, that fraction with 3 numerator terms can be written as the sum of 3 fractions, x squared divided by x plus 3x divided by x plus 2 divided by x. So the divisor divides all 3 terms of the numerator. And when you simplify, you get x plus 3 plus the fraction 2 divided by x. And again, when x is come back. When x is large, positive or large negative, in other words, the magnitude of x is very large, then the fraction 2 divided by a large value is going to be close to 0 and go to 0. So we draw that arrow and 0 to mean goes to 0. So let's go back to the quotient x plus 3. The expression x plus 3 is the expression for the equation of the asymptote or boundary line. And it will be an oblique asymptote, OA, oblique asymptote, or boundary line with a slope to it, is going to be y equals 1x plus 3, right? That's the quotient polynomial. Therefore, the slope, m, is positive 1, and b, the y-intercept, is 3. All right, let's go back to the handout. So step 5 was to determine if there's a horizontal asymptote. No, because that's case 1, where n is less than m, or case 2, where n equals m. We have case 3, and an oblique asymptote, OA, y equals 1x plus 3, we found by division. So we can draw in this boundary line who's going to intersect the y-axis at 1, 2, 3. Have a slope of 1, so we'll run and rise 1, run 1, rise 1, and repeat that. Run to the left and down 1, run to the left and down 1. So the oblique asymptote is this green dashed boundary line with the slope of 1 and b equals 3. All right, y-intercept is none. So now we need to do step 6, which is to get more points. Let's do step 6 over here. more points, which may require a calculator. But on a test, if you have the main concepts and know that the graph approaches boundary lines or asymptotes, a few points will be enough. Now, when you want to get more points, you have to decide, what am I going to plug in for x? So if you look at the graph here, it says, well, maybe we should pick some values like -4. And in between -2 and -1, you might pick -1.5, -1.5. Between -1 and 0, -0.5. Now on the other side of the y-axis, in quadrant 1, choosing x equals 1 would be a good choice. Let's choose 2. And by the way, 1 and 2 would be pretty easy by hand calculations. 3 is not so bad. X is 3. And that should be enough points. So when x is -4, we have y, or function value is -1.5. -1.5 is about +0.2. -1/2 is -1.5. Again, 1 we could do by hand. 1 squared plus 3 plus 2 divided by 1 is 6. When x is 2, we have 6. Again, 3 and 6.7. All right, so let's plot these points. -4 and -1.5 is about here. -1.5 and 0.2. Now that's approximate. In calculus, you learn to find the exact coordinates of that local max, that peak point. And now, since we know the graph approaches boundary lines, from the local max, or the top of that peak, will go x to the left, x approaches -infinity, and the graph will approach this oblique asymptote whose slope is 1. And so the function value gets closer and closer to the value x plus 3, right? Because the oblique asymptote has equation y value is x plus 3. Then from the local max, or the peak, we'll have a turning point. And again, in calculus, you'll find the exact coordinates of the turning point. And the graph will never intersect a vertical asymptote and approach get closer and closer. X cannot equal 0. Now on the other side of the y-axis, we have x is 1 and 6. And 2 and 6. 3 and 6.7. Now, if you're not sure, you can always pick a couple more points. If we wanted to, we could pick like 1.5 to find an approximate pair of coordinates for the local min, the turning point. Matter of fact, let's do that. Let's evaluate for 1.5, positive 1.5. You get 5.8, which is going to be the approximate y coordinate for the local min, or turning point. So let's graph that point. Be about here. And since we know the graph will approach asymptotes or boundary lines as x goes to infinity, the function value will approach the value of x plus 3 from the equation of the oblique asymptote, and the graph does something like this. And as x approaches 0 from the right, y will go to positive infinity. Positive infinity is the opposite infinity, which on the other side of the y-axis, as x approaches 0 from the left, y goes to negative infinity. That completes the graph. Let's go to number 4. Analyze the graph of the rational function r of x, whose leading coefficient in the numerator is 1, whose degree n equals 2. Denominator leading coefficient is also a positive 1, and m is equal to 2, which is equal to n. So n equals m is the case 2, where if n equals m, we're going to have a horizontal asymptote, which means boundary line, where the function values are going to approach the ratio of the leading coefficients 1/1, because when x is very large, the leading terms are going to be much larger than all the other terms. So the function values or y values are going to be approximately the ratio of the leading terms because they're so much larger than all the other terms. But x squared divided by x squared divides and cancels out for any value of x, even when x is very large, negative or positive, and this is equal to 1, right? Because x squared over x squared cancels out, and 1/1 equals 1. So y equals 1 will be the equation of the horizontal asymptote, which comes up in step 5. All right, step 1, factor if possible, the numerator or denominator. Now the numerator may look factorable, but if you try to factor it, you would see that you can't. The numerator is prime, but you should try it just to be sure. Try to factor it. Denominator is a difference of two squares, which factors as a product conjugates, plus 1 minus 1, and the denominator zeros, -1, +1, have multiplicities that are odd, which means the graph will have opposite infinities as x approaches -1 from either side, and as x approaches +1 from either side, the y values will go to opposite infinities. R of x will go to opposite infinities. Part of step 1 is to state the domain, which is all reals except, we can write it this way as well. X cannot equal -1, x cannot equal +1. In step 2, you would divide and cancel if possible, but not possible here. No simplifying possible. Step 3 is to state the x-intercepts and y-intercepts. So for x-intercepts, y would equal 0, or r of x would equal 0, which occurs when the numerator is 0. So if x squared minus x plus 12 equals 0, then we'll have x-intercepts. But when you try to solve for x to get x-intercepts here, let's go to the discriminant test, which is b squared minus 4ac. This will tell you if there are two real zeros or two non-real, imaginary zeros. Well, b squared is -1 squared minus 4 times a is 1 times c is 12, which is 1 subtract 48, which is a negative result. So because the discriminant value is negative, that would mean the two zeros of this quadratic, which are coming from the numerator, are not real, are imaginary, are a pair of complex conjugates, which means the graph has no x-intercepts. The graph will not cross the real number line because there are no real zeros for this quadratic of the numerator. Conclusion, therefore, no x-intercepts. If there's a y-intercept, then x would equal 0. So we evaluate r of 0, plug in 0 for x. All variable terms become zeros, so we get numerator 12, denominator -1. So the y-intercept will be x is 0 and y is -12. Step 4, state the vertical asymptotes, VA, which come from the denominator zeros. The equations of the vertical asymptotes are going to be x equals -1 or +1. And those are boundary lines we can start to put into the graph. X equals -1, x equals +1, no x-intercepts, and y-intercept is -12. So on the y-axis, we could change the scale. So every horizontal line is 2 units. So -12 would be down 6. So -2, -4, -6, -8, -10, -12. Here's going to be our y-intercept. All right, step 5, determine if there's horizontal asymptote, which occurs if n is less than m, not the case here, or if n equals m, which is the case here. So step 5, let's say since degree of the numerator equals degree of the denominator, that means we're going to have a horizontal asymptote whose equation is y equals the ratio of the leading coefficients, the ratio of 1 to 1, which equals 1. So y equals 1, its graph is this horizontal line going through y equals 1. All right, step 6, we need more points. Let's do that here. Step 6, let's do an XY table that's horizontal. Input x, calculate y, or r of x. So based on the graph, we'll decide to choose integers, possibly decimals like -4, -3, -2, maybe we'll see what happens at -0.5, +0.5, 2 and 3, x is 2, and x equals 3. So this looks like probably would use a calculator here in homework. -4 input, we get 2.1 as a y value. -3, we get 3. -2 is 6. -1/2. -16.3. +1/2. -16.3. X is 2. 4.7. X is 3. 2.25, 2.25, 2.3. All right, so let's graph these points, -4 and 2.1. About here. -3 and 3. We're starting to see some curvature here. -2 and 6. That would be enough points because we know that the graph will approach and never cross a vertical asymptote. So the graph will do something like this. As x approaches -1, r of x goes to positive infinity. And then right to left, as x goes to negative infinity, the function values will approach the value of 1. So the graph approaches the horizontal line, y equals 1. Now, around the origin, we have -0.5 and -16.3. So we have -12 graph, -14, -16 is roughly in here. And then when x is positive 0.5, we have -16.3 approximately there. Well, it's going to be a little lower than -16. So let's drop it just a little bit below, something like that. So it appears the y-intercept is a local max, and since as x approaches -1 from the right, we'll have the opposite infinity. R of x goes to negative infinity. We know the graph will do something like this. And as x approaches +1 from the left, it appears the graph will have a turning point, local max at the y-intercept, and do something like that. Let's graph a few more points. X is 2 and 4.7. It's about here. And then 3 and 2.3 is about here. All right. So because of the denominator 0 of +1 having odd multiplicity, we know that on the right side of x equals 1, the graph will go to the opposite infinity, which is positive infinity, and never cross a vertical asymptote. And as x gets large positive, x goes to positive infinity, the function values will approach 1, and the graph will approach y equals 1. So something like this. Now, it's an interesting question. Does the graph intersect the horizontal asymptote y equals 1? The answer is it does cross at 13, 1. That would be kind of an extra bonus question. The graph of the rational function intersects the horizontal asymptote y equals 1 at x is 13 and y is 1. And you can show that by solving the rational expression equals 1. So you set the fraction for r of x equal to 1, or 1 over 1, and then you cross multiply and solve, you'll get x equals 13. So to represent that, we're going to put 11, 12, 13, and the graph will do something like this. Now, on a homework or test, this would be sufficient, but if you want to go the extra mile, you can show that the graph crosses over or intersects at 13, 1, about here. All right, and we're in the graph there. Example 5, analyze the graph of the rational function. And initially, step 0, let's call it, we have x minus 1 to the first power. let's just rewrite it over here. So r of x is x minus 1. So that's a numerator 0 of positive 1, and a multiplicity 1 that's odd. X plus 2, so numerator 0 of negative 2, multiplicity that is even. Now with even multiplicity in the numerator, the graph will be tangent at negative 2. Then denominator is 0 of 0, odd multiplicities. So the graph will have opposite infinities as x approaches 0. And second, denominator 0 of 4. And because the multiplicity or exponent is a 2, we're going to have same infinities as x approaches 4 for the denominator 0 of 4. Degree n of the numerator is going to be 3, because if you multiplied out the numerator, you'd have x to the third as the greatest exponent is 3. And the denominator, greatest exponent on x, if you multiplied it out, would be also 3. So m equals 3. So n equals m. This is the case of horizontal asymptote. This case 2. Horizontal asymptote's equation is y equals the ratio of the leading coefficients, which are positive 1 in the numerator, positive 1 in the denominator. So 1 over 1, which equals 1. All right, so those are the initial details. Then we do step 1, which is to factor, which we've done. It's already in factored form for us, so we didn't have to do any factoring. So let's just say factoring is done. Part of step 1 is to state the domain, which is all real numbers excluding 0 and 4. Step 2 is to divide and cancel if possible, but simplifying is not possible here. Step 3, find the intercepts, x-intercepts and y-intercepts. So for x-intercepts, on the x-axis, y equals 0 or r of x equals 0. And r of x equals 0 when the fraction equals 0, which occurs when the numerator equals 0. So we have x equals 1, or x equals negative 2, but that repeats twice. So we have a double root or root of multiplicity 2. So we have x equals 1, x equals negative 2, x equals negative 2 a second time. A repeated root, but only 2 x-intercepts. So let's mark those intercepts at positive 1 and negative 2. Y-intercept, let x equals 0, but we can't because 0 is not in the domain, right? So let's say that however, X cannot equal 0. It's a restriction. Therefore, there is no way to evaluate R of 0. R of 0 is undefined. And therefore, no y-intercept. All right, step 4, vertical asymptotes. Vertical asymptotes occur when you have denominator zeros, such as x equals 0, which is the y-axis, and the other denominator 0 is 4, so x equals 4 is the second equation of the vertical asymptote, and we can draw those in now as dashed lines. So we have the y-axis, x equals 0 is 1 vertical asymptote, and x equals 4. Step 5. Since the case is case 2, where n equals m, degree of the numerator equals degree of the denominator, means we have horizontal asymptote, y equals 1, so we can draw in this horizontal asymptote. And now we need step 6, which is more points. So for more points, let's choose to input x and calculate function values. Let's input -4. The output is positive 800ths, very small, close to 0. -3, even smaller, positive 300ths, close to 0. -1, back to 800ths. -1/2, positive 0.3, 3/10, increasing. X is 1 is an intercept. Positive 1/2 is -0.51. X is 2, function value is 2. That one probably could do by hand, plug in 2. X is 3, 16.7. X is 5, 39.2. Let's just say 39. 6, 13.3. And let's go to 10 and 3.6. All right, let's graph these ordered pair solutions. -4 and 8, positive 800ths. Very small, close to the x-axis. -3, 0.03, 3/10. A little higher up. -1, 0.08 again. Now remember, at the x-intercept of -2, -2 as the numerator is 0 had an even multiplicity, so the graph is tangent at -2. So let's make a note here that the graph will bounce up at -2. So it's going to do something like this. It's going to just be tangent. It's going to be hard to draw, but something like this. Right? Just bounce, be tangent. And then it goes down to positive 8/10. And then as x goes to negative infinity, the function values approach 1. So let's see, we can represent that happening. Approaching positive 1 as x goes to negative infinity. All right, back to plotting points. -½ for x and y is 0.3. We can never cross the vertical asymptote. So what's the graph going to do? We would need to plot more points to know the graph does the following. The graph is going to turn up, intersect the horizontal asymptote, and then y goes to infinity. Now, this is an interesting question. How can we figure out that the rational function's graph intersects the horizontal asymptote y equals 1? So let's make note of this. How do we find this intersection point where the graph of r, the rational function, crosses y equals 1? How can we show that really happens? So to do that, we solve r of x equals 1. Function value r of x is equal to 1. So we're going to go to another writing area, and we're going to set r of x equal to 1. Let's do that here. Okay, so we're going to solve r of x equals 1 to find intersection point coordinates. So x minus 1 times x plus 2 squared divided by x times x minus 4 is equal to 1. For what value of x? Now 1 is 1 over 1, so we can diagonally crisscross multiply. That's the cross product rule. Cross product rule says in a proportion, two equal fractions, you can diagonally multiply to get a cross product. And the other cross product is 1 times x minus 4. All right, let's multiply things out. So we have x minus 1, x plus 2 times x plus 2 equals x squared minus 4x. Let's do x minus 1 times, let's FOIL these out here. X plus 2 times x plus 2 is x squared plus 4x plus 4 is equal to x squared minus 4x. Distribute the x, so x times the quadratic minus 1 distributes times the quadratic equals x squared minus 4x. Keep multiplying, so we get a cubic, x cubed plus 4x squared plus 4x minus x squared minus 4x minus 4 equals x squared minus 4x. Let's simplify. Plus 4x minus 4x. So we have a cubic, x to the third. 4x squared subtract 1x squared is 3x squared. So that'll take care of those two terms. Now on the right side, we'll subtract x squared. And then from the right-hand side, we'll add 4x. And then minus 4 is set equal to 0. So we have x to the third plus 2x squared plus 4x minus 4 equals 0.